The plan for today is to do some reviewing of the shapes, which people typically need a little bit of review of the shapes. It's not easy. So we're gonna do a little reviewing of the shapes. Then I'll show you a demo that kind of shows where polar, non-polar, how it works. And then really the last half hour about is a simulation working with polar, non-polar things to try to. It's a concept that a lot of people struggle with. You may have heard it in the past, but people typically don't get it coming into this. So hopefully that simulation helps. Homework-wise, I have nothing there because I'm hoping you get the simulation done. Those of you that need to leave early, you're definitely not going to, so you're gonna have homework. And some of you might not get it done, but the majority of people when they left first block had it done. That kind of just depends on how fast you move through the simulation and drawing the different, you're not drawing a ton, but putting different things on the little handout they have for you. So some of it, some people will leave with none, some people will leave with some, just because it's on how fast you move through that. Monday, we will apply all of it to your little structure sheet, how to draw dipoles, how to determine if they're polar or non-polar. After that, we will then compare and contrast all the bonding, and I'm going to add one to it, metallic. So metallic, ionic, covalent. And Tuesday, quiz. After the quiz, we will finish up the, so that's the last quiz of the unit. I noticed there's at least 4 more, no, there's going to be 8 or 9 this quarter. I need to decide, depending on how time things go, and if we have any snow days or anything like that, the very, very last chapter, if there's a quiz or not. But there will be 8 or 9 quizzes this quarter. Tuesday, yeah, I already said that, we'll do the quiz and hybrid orbitals, and then review and get ready for the group quiz on Wednesday. Wednesday, can't even off to a quiz. Thursday, review, game, activity, haven't decided yet if we're gonna make it a game or what we're gonna do with that. And then Friday, test, chapters 9 and 10. Again, there's a lot there. It's just been a long time of start with electromagnetic radiation. And using those 2 equations for speed of light, or with the speed of light, wavelength, frequency, it's been a while ago. And then doing electron configurations and orbital diagrams and all that stuff, and now with bonding. So there's a lot going on there for that first test. And then before Thanksgiving, because that brings us to a 3-day week, we'll do gases is where we'll start there. So some of that's going to be review, and some of it not. But start labbing again. Yeah, we need more lab. We need another lab. We had a lot of labs, and now it's been kind of a drought. So we're going to feud real quick. We have table, we have 3 questions today. Table 1 is going to get to go first again. So we'll mix it up real quick. And table 1, here's your question. Or everybody, here's your question. How old would you like your first child to be before their first date? How old would you like your first child to be before their first date? 7 answers on the board. 7 answers on the board. Table 1 gets the first chance.
16.
16 is the second most answer with 25 people. 18 is the first answer with 27 people.
That's depressing.
What do you guys think? 17 is number 5. 7 people said that. What do you guys think? 15. Whoa. What do you think? Make the decision.
Okay, 13.
13 is last on the list with 3 people.
Oh, yeah.
Here we go.
15.
Spokesperson. What's that?
15.
15 is third on the list with 28 people. What do we got?
14.
2 left. 14. 10 on 10 people said that. And the last one. What do you guys think?
19.
No, not on the list. 1 left on the list. What do you guys think? 12. Ouch. No, not on the list. Not ouch, but hey, it's not on the list. 21 is on the list with 4 people. 4 people said that. All right, table 2. Table 2 gets the first chance. Tell me a type of gun that doesn't shoot bullets. Okay, type of gun that does not shoot bullets. Type of gun that does not shoot bullets. A Nerf gun is...
It technically fires Nerf bullets.
I'm so proud
It's not on the list. Okay, not on the list.
Water. We're gonna go with
Water
water.
gun has 18 people said it, third on the list. There are 7 answers on the board. What do you think?
Laser gun.
A laser gun is not on the list.
Laser gun. Cap gun.
Cap gun, not on the list.
A glue gun.
A glue gun. It's actually
That's a good answer.
good answer, but sorry, not on the list. Paintball is only 2 people though.
Oh, that was
Stun gun is second on the list with 21 people. Huh? A finger gun, no. 5, 4. BB gun, yes, 14 people. That was 4th on the list. There's still 3 answers remaining, including a top 1.
Pellet gun?
Pellet gun, no.
That's a BB.
Marshmallow gun?
Pellets and BBs
Huh?
are different.
Marshmallow gun?
No.
They're different. I have a pellet.
Is that a thing?
No. 3 on the list, including the number 1 answer. 5, 4, 3,
Airsoft.
1. No.
Like the
That's a pellet and one.
No. That's a good answer too.
Can we go around?
Wait a second, we've gone through twice already?
Yeah.
Yeah, go around again.
Wow. Number 1 answer.
Can we go around
Just
again?
because the number 1 answer is they're not there, yes, let's try it. No staple gun. 5, 4, 3, 2. Next table.
T-shirt gun?
T-shirt gun, no.
That's a cannon.
Whatever. Cannon.
Huh?
Nail gun.
Nail gun is a number 1. Still 2 left.
Wait, how much was that?
These are, whoever
23 people.
Wow, we're just such zoomers.
2 more left.
We're zoomers.
Anyone?
Yeah, confetti gun.
No.
Rubber band.
No. We started at that table, right? Anything? No. Good answer though. Biceps / muscles. Obviously. Done. And even a dumber answer, son of a gun. And the last one. Hey,
Those would be worth it.
I know they're not gonna answer. Name someone, this table's first. Name someone you might ask for directions, quickly. Who wants you ask for directions?
Wait, who should?
Name someone you might ask for directions. A tour guide. Not on the list.
A local.
A local. I'm gonna give you that on stranger / pedestrian, because if someone's just in the area, I can see that, okay? I'll give you that. Here, you might ask for directions. 10 points. Who?
Phone.
Phone. Siri / app is second on the list, yes. 19 people. Family. I'm gonna give you parent, which is 2 people only said.
If you're lost, I don't know.
Anyone? Is there anything? 3 answers are taken and there's 5 more left, including number 1. A map. No. A cop. No. Table 2. Enough of the word. Yeah, let's go. Huh? Uber, no. Might you ask for directions? 5, 4, 3.
Crossing guard.
Crossing guard, no.
Well, it was worth a shot.
5, 4, and 3, 2.
I don't know, ranger, park ranger.
No. Number 1 answer still on board. Bus driver. No.
Police officer.
Already said a no.
What? Who said that?
Someone back there. Table 7. Thinking. 5, 4, 3, 2, 1. Anything?
Travel agent.
Travel agent, no.
Cashier.
Give it to you. Gas station employee. 16 people said that. Still not the first person. And table 2? Anyone? 5? Grandma? No. Alright, so we're going to be done. Number 1 on the list with 20 people, just a friend. Hey, how do I get to Target? A store owner, a priest, ask for directions in life, I guess. And a neighbor.
I would all.
You didn't say directions on where you're going. As far as with your car, it just said directions.
Everybody takes it.
You never know how people are gonna answer. Alright, here we go. Quizzes from yesterday. Quizzes. You probably got off real quick. Here we go. Ava not here. Maggie, Grant, Shelby, Connor, Lauren. Connor Haffer, sorry. Lauren, Louisa.
Everyone answers. Who are guys?
Carter.
No, it's up there.
Michael. Connor Boat.
Fast on your wall.
Carter Larson.
Belfast. I was like, Belfast?
Peter. Julia. Sydney. Emma. Taylor. Amber. Sydney C.
What the heck is that?
Maddie. Luca. Ben.
I can't say that.
Maddie. Juliana. Jaden. Dalton. Bo.
3 down. I don't really care. What'd you get?
I'll be here. Deborah, Ellie, Haley,
I feel good about
Gus,
yourself.
and
My
Luca.
stats that's like. I'm giving you permission to look at my
Again, lots of good pictures. Tough decisions. All right. The fan is on. There is a smell in here, and it's not me. I don't know if someone has a bad stomach today, but hey, the exhaust is on. Let's go through it. Let's go through it. It's my solution right now. No one knows. Number 1, aluminum or bromine, AlBr3, because aluminum is +3, bromine is -1. Number 2, that structure would have oxygen, well they all have oxygen in the middle, but single bonds to hydrogen and 2 lone pairs on the oxygen. Number 3, single is smaller than double, or bond strength is weaker than double, which is weaker than triple. Triple is the strongest. Number 4, 32, because phosphorus has 5, each of the options have 6, so that leads to 29, and 3 minus means 3 more, so 32. So, I have really good English here. How will the ratio of zinc to phosphide ions in zinc phosphide? So the ratio of zinc to phosphide is going to be 3 to 2, because zinc's a +2, phosphide's a -3. Those zinc and silver ion charges are still going to get you. Number 6, resonance. All of them will have single bonds except, some of them takes a little time, but the only one that, if you do the little structures, the only one that has double bonding would be ozone, which is O3. And the reason why is because there is 18 electrons. If you try to put single bonds and fill in the octet of all of them, it doesn't work. So you need to put a, that was not smart, let's put that there. You need to put a double bond somewhere. I just put it on the right randomly, it could have been on the left, that means there's resonance. So there's two good structures here, where one, it could be here or it could be there. Next one, if we look at two atoms sharing means covalent, unequally means polar. Unequal means polar, that's the old polar bear and penguin part that we talked about. Number 8, few issues here. First of all, calcium. Some people showed the 2 dots on one side. That is not correct Lewis dot diagrams. Same thing with the oxygen. If you had 2, 2, 2, that is not correct Lewis dot diagrams. Some people made a mistake on one or the other. And I tried to correct those as much as possible during our practice. So they'd be on separate sides. The oxygen would be 2 on one, 2 on the other, 1 on the other. Move that electron over, move that electron over. Now, there's charges. Not before that. These guys don't have charges. Only once the electrons move. Now you have that next step where the non-metal has 8 electrons, and there's now charges. So, if you didn't put charges at all, I took off more than, some people put charges before and after, which is not the case, but at least you put it after. But before they don't have charges. And some people put charges only before and not after. So it's a lot of range of taking look at a lot of little things that could be issues on that one. The next one, probably the biggest issue, if those things weren't the same, was the fact that silver makes a +1, so it only has 1 valence electron. Nitrogen has 5, and this would be the arrangement of those 5. It doesn't matter where the lone electrons are, but you need to have at least 1 on each side. Think about it like Hund's rule. 1, 2, 3, 4, and then it starts doubling up 5. So 1 goes there, we need another silver. 1 goes there, we need another silver. 1 goes there. And afterwards, Ag3 with a 1 plus, N with a -3. Charge and dots. That's supposed to be a 3 out of 5 for a charge. -3 and dots. And if you have questions on yours, just let me know. If you're wondering what is different compared to what I just did for those. But I really tried with our practice to try to get rid of those little tiny issues that were happening. But I had a few people that took 8 and 9 as Lewis structures, and they try to make single, double, or triple bonds, which is very different than an ionic bond. Which number 10 and 11, these are now covalent bonds. So show the Lewis structures here. Count up the electrons, see if you have single, double, or triple bonds. In number 10, they'd all be single bonds. So whichever one you picked, put carbon in the middle, single bonded to 4 fluorines, there'd be 3 lone pairs around each of the fluorines. BH3, single bonded to all the hydrogens. No lone pair on the boron because it's good with 6. If you had NCl3, and in the middle, single bonded to all the chlorines, there'd be a lone pair around the nitrogen and 3 lone pairs around each chlorine. Number 11, again, all single bonds. We needed brackets, it was an ion. But for H3O plus, O in the middle, 3 single bonds to the hydrogens with a lone pair on the O, brackets, NH4, and in the middle, 4 hydrogens around it, single bonded, brackets. SO4 is when we did on our sheet, S in the middle, single bonded to all the 4 oxygens, and 3 lone pairs around each of the oxygens. So, your questions on yours. Got a few people already retake it this morning that wanted to. You can if you want, but we do have more quizzes, so you can kind of make a decision on when you'd like to do that. Questions on yours, let me know.
Look at my picture.
I'm looking, I'll take the you. So short, you know.
I wasn't aware. I'm not watching the movie. They're first.
Not just like.
Yeah.
I don't think American history is.
No, not sure, can't do that anymore. Can't do that anymore, not that.
Everyone wants to slide. He doesn't like it.
Oh, yeah.
Why?
Because I avoid
That
him.
charges my name as a string track.
You know what? I deserve that.
You guys should make a sign like that, go.
Alright, people. So, yesterday, we did.
I slack.
So yesterday we talked shapes. I've laid them all out here just to kind of refresh your brains, but we're gonna review them a little bit. So we have our shapes, you don't need to take that thing out, we're just gonna look at them and then you're gonna do a little thing with that. But if you have 2 atoms only, it has to be linear. Then you have another situation where you have 3 atoms, but the center atom only has 2 regions around it. Reminder, an electron region is either a lone pair or any type of bond. That's an electron region. They're going to repel each other equally according to VSEPR, the valence shell electron pair repulsion theory. Then you have trigonal planar, where there's 3 regions around it and they're all bonding. What if you have 3 regions around it and only 2 of them are bonding? Well, then you have this bent shape. If you have 4 regions and all of them are bonding, that's tetrahedral. Refreshing brains. If there's 4 regions and 3 of them are bonding, there's a lone pair up here, that's trigonal pyramidal. Someone asked this morning, or said chemthink look very similar, or they look the same, pyramidal versus planar. They are not. Planar, they're all on the same plane, which is going to matter because that means it's going to be non-polar as we move forward. This will be polar because there's 1 atom on the top and 3 sitting at the bottom. That atom should be sitting up in the air. Then 4 and 2 bonding makes it bent. 5 with trigonal bipyramidal, 6 with octahedral. So just a little refresher, leave those up. Once you're making them with jelly beans and toothpicks and stuff, you won't have those, but just trying to review and get to know these things as much as possible. Tuesday's the first time you will need to know some shapes. So a little review I would like you to do with your people about shapes. And partially it's just to kind of try your own Lewis structures, review those, and try to name some shapes again on your own. See what you can do with just the sheet. The thing you had yesterday, or actually there's plenty of information on a sheet. You don't need the thing from yesterday. You're going to need a periodic table, though, to do those structures. But then on the very back, it's looking at big molecules, because this still applies to big molecules. Even though we're just naming the small molecules, the angles all happen with big molecules. Shelley?
Why can't we see the whole hair? Yeah. Why is it invisible?
Oh, they just don't have a spot for it. Like with these guys, atoms aren't built to have a lone pair. These guys are though. Depends on the model. Like this one. Like, these are modeled the same thing. This one shows that stick doesn't compare, just this doesn't have it. Depends on what model you're using. So like on a jelly bean thing when you do on Tuesday, some people are like, well, do we need to show lone pairs? And people say no, but some people want to. They'll put toothpicks into the lone pairs because it makes more sense to them. Just depends on what you're looking at. You know, those who will dispose of the jelly beans as you see fit.
Are they like?
Kind of no version.
They are.
They're either going to be like your tables, or you get to pick groups, or some will pick, and people don't do the review, get to be together. I've done that before. Well, it depends on my feel. I feel that day. Give it a try, give it a try, give it a try.
Well, you want to just like not do it, you want not do it.
That's true. I don't have patience for you. be bonding all of our electrons.
I'm unorganized. I actually
Your
don't
folder, are you dedicated to a folder?
No, it's I don't know. I just always get told that you got that shit. So I
What,
should.
oh, like that.
Yeah, I should change. I know I should. No, I should. Like,
Can you find stuff if you need?
I mean, I can do some of that stuff. It's like that off chance, you know, I'm like, oops, can't find it. So. But like most of the time, 95%. So.
5%.
I feel like I wouldn't say.
Can you find stuff you need?
Oh, I have all my
It's like
classes in a
class,
folder.
it's paper from classes all the way back to the start of last year. It's just
All in there.
Wow.
Surprising, it's not like.
more stuff. Through all the stats.
I don't even have enough
We got some Lewis structure practice and from that naming practice. Kind of all go together. Nothing? As far as I know, it only connects this. And there's a camera right there.
Yeah, I was just gonna say, why is it camera?
Dr. Brunder has these, 30,
Where there's a long pair.
just sometime about,
No, is it this one?
like, either he has to come in or a video of it's like,
Yeah, that's what I was gonna say.
of what we're doing in here. And
Cause they're gonna have like a.
Ava's gone and I want a video of like, the same thing. Yeah. It's recording Jaden, especially.
Jaden?
It's actually, it probably doesn't see you at all.
Yeah, because if you're gonna get 16, but you're gonna have
But that, I was so
No, it doesn't,
excited
can't see
about
you.
that. I was like,
Just Haley.
Shelby, oh no, that makes me. You got it. No,
Come on, people, come on, come on, come on, come on.
Ask Peter.
Keep trucking, keep trucking.
Oh, I
no,
know.
I don't care about
Now let's try it, give it a whirl. You're gonna need them. To do what? Have fun. Also electrons.
Isn't this person just linear?
it sucks that it's closed. I won't tell you.
Peter, you're saying.
Ben.
Wait, hold me a second.
It is, there's not a ton of space. But there's a lot of space in the bottom.
Gary?
I know there's not a lot of space by those little structure areas, you need to put it on the bottom, just wherever, just practice. There's not a lot of space in the little structure areas, put it on the bottom if you have to, or wherever you can. Practice, practice, practice.
Because with oxygen, it has two.
Will you please stop? You don't have to bother me here about. Oh wait, they're hurt. I don't know. I don't know. I am not in
Where's
a.
I love to metal, okay?
I gotta.
Like it's not.
Don't stop. It's not good for you.
The sulfur has.
It's how we bond with.
I don't talk to like great bombs.
Oh no, I got.
Burn bridges.
No. I love these dots around the sun.
Oh, don't you? Peter around. Just joshing around. Not maybe chatting.
Did you hear that?
That's 20. There's. Wait. Oh, wait, there is a number. I'm stupid. Oh my gosh, you're right. It's just a dump on
That's what my sister says all the time.
16 plus 7.
23 and this. Yeah.
Yeah.
So, yeah.
What? Wait.
That's H2. Two
Grant? NO2. How many electrons should that have? Should I have 24, shouldn't it? Right, Notch?
NO2,
NO2.
12 plus 5 is 17 plus 1 are 18.
12.
2 for the oxygens. For 2 oxygens, 6 apiece.
I need total electrons.
Oh.
Peter.
Not
Peter,
bad.
So 6 plus 12 plus 5, 17, 18. So there needs to be a double bond.
How do you know it needs to be double bond?
So these both of
Even in that 80,
Oh yeah. Always doubles. Yeah. It's pretty high.
4 is a technique.
Yeah.
there's a lot.
We have to memorize it.
You should just get a hydro flask and drink school water. Tastes like you're drinking
How about what?
Yeah, so last year they.
water out of hydro flask.
Oh.
Yeah, that's beef.
Actually, no, never mind.
It's like so badass.
What?
6, 6, 6.
Like 666. Oh my god.
Smells like drugs.
Actually, this is not my business. I'm making it my business.
It's up faster.
I'm sorry. You don't have to tell me if you don't want to.
What's up?
But if you want to know my team, then okay. I'm gonna go see if anyone.
Oh, why did you
I'm going to see if anyone. Don't walk away.
So some of you are done and some of you are not. Do 3 minutes and start going over it. Do structure and shapes practice.
Hold it.
valence electron test?
Oh, 7. What is it? Valence shell.
Yeah, that's what I was talking about.
Yep. So on the back, we're just looking at groups of electrons around an atom. So this is four groups of electrons, so that's be 109. This atom has 3 groups of electrons, so it's a bonding pair. So they're gonna say 120, because they're just looking for you to say 109, 120, that's it. So what the approximate angles might be.
Did you become a doctor?
I don't know, it's a chemistry degree, but it's
Sooner enough. Yeah, so you assume single bonds, don't draw all the dots like you're doing.
It's expensive.
Oh,
Okay, what?
but then I can, assume single bonds. And start drawing.
Because it has a long hair.
No, I heard about
I don't know who will buy it. That paycheck is here, so.
That's a good look.
So that, so it's not an improvement,
Bond is just a group of electrons, so like this carbon. This carbon has 1, 2, 3 electrons around it. So it's still 120.
even 109.
So if you go regions, well, like,
Look, you have to.
You know, that's. We get a 106.
You only have to write 109.
No,
It's says
because age
read the instructions.
Oh.
Yeah.
all right, folks. Let's go over it. I know some of you are not done, and some of you are done, and you're waiting. We're gonna go through it quick. If you're struggling with the Lewis structures, we do want to practice, because here's why. If you can't make a Lewis structure, you're not gonna be able to get the shape. If you can't get the shape, you're not gonna be able to tell if it's polar or non-polar. Can't tell, and then you're also not gonna be able to do hybrid orbitals. So a Lewis structure drives a lot of things the next few days. So practice the Lewis structures if you're struggling with that. Again, quickly the steps. You put the lone atom in the middle, the others around it. You count up your valence electrons, total them up. You assume that there's a single bond. And then fill in the lone pairs around everything. If there's single bonds work, that means all of them have 8 and your total electrons work. If you don't have enough electrons, then you have to start doubling up, which we'll talk about here in a bit. Please take a look up here, even if you're on the back, look at the front real quick. So I'm going to answer one of the questions just from these pictures real quick. From these pictures, it is showing where there's 4 regions of electrons, but there's lone pairs and then there's 2 lone pairs, or a lone pair and 2. The angle is not exactly 109.5 each time, but it's around 109. And the reasoning is because these lone pairs take up a little bit more space. And by more space, they're a little closer to this atom, and they push this angle a little tighter. You're not going to have to memorize these exact angles, but they are a little bit smaller because the lone pairs are squishing them together more. So that one question about the lone pairs, they take up a little more space. Same thing here, it squishes this angle a little tighter because it's pushing those electrons closer together. So instead of being 120, it's a little bit less than 120, but it's about 120 still. So if we go to the next, what's an electron region? What do you guys think about that? Luca?
We just did where like electrons are.
That is fine. That would be a bonding electron, whether it's 2, 4, or 6. So a single, double, or triple bond, or a lone pair. Sounds good. Maggie, what about a lone pair region?
Not being shared or bonded.
Not being shared or bonded. That sounds good. Or 2 electrons not in bond, something like that, whatever. Bonding region would be a single, double, or a triple bond. So 2, 4, or 6 electrons would be considered bonding regions. Looking at the total regions, what about 105 to 109? How many total regions? Sydney's C?
4.
4. What about approximately 120? Sydney M. 3. And approximately 180 would have how many? Julia? 2. Yep. So then I've changed this up, and the reason I changed this up because all 3 of these were already on your practice sheet we just did the last few days. So I wanted you to see something a little different and try something new. So with the first one, again, thinking of the process, we have an N in the middle, O's to the outside. There's 18 electrons to work with because there's 5 from nitrogen, 6 from each of the oxygens, plus this -1 charge means there's 1 more. That means 18. I assume single bonds, but when I do that, I don't have enough electrons to give 8 to nitrogen. Henceforth, art thou, there is 1 double bond. 1 double bond. This would be a resonance situation also. There is 1 double bond. What would the shape of that be, Peter?
That'd be bent.
It would be bent, yeah. It'd be like this guy right here, where we don't see the lone pair at the top because of the way this model is made, but there'd be a lone pair up at the top here, and the oxygens at the bottom with the sulfur as the pink atom, or sorry, the nitrogen. PCl3, I would have P in the middle, put the Cl's to the outside. Count up my electrons, I have 5 from phosphorus, 21 from the chlorine, so 26 total. When I do that, I can do this single bonded, assume that, and then I put in all the lone pairs on the chlorines and a lone pair on the phosphorus, and 26, it works. Single bonds work. Connor B, what shape did you guys think that was?
Trigonal planar.
Trigonal pyramidal. Yeah, because a lone pair. If this lone pair wasn't here, it'd be planar. But with that lone pair there, that's going to push those other those chlorines down and be trigonal pyramidal. And this last one, and I know you didn't have much space, so that's what I was saying to try to put it on the bottom if you needed it. The last one ends up with single bonds again. You have 32 electrons to work with, and when you make single bonds and put lone pairs around all the fluorines, voila, it equals 32. So single bonds work. What would the name of the shape of this be? Michael, what did you guys get? Tetrahedral it is. 4 around it, and all 4 are bonding. Number 6. Need to get the structures. So again, lots of Lewis structure practice. Some of you really need it, and you need a shapes practice. So that's why I'm going back to this rather than just moving forward right away. Hopefully this helps. If not, I can give you more help. I had someone this morning saying, okay, I need more Lewis structure practice. So she said, do you have another sheet? Or is there more that you can give me? And she's like, oh wait, maybe the book has a bunch. And yeah, she looked at the back of chapter 10, there's a whole bunch of practice ones you can do. That's a good place, but if you want more, just ask. I'm happy to give them to you. So if SO2 is going to have a single bond, it's a lot like the NO2 up here. There's a single and a double. SH2 looks a lot like water, which makes sense because H2O has oxygens in the same group as sulfur. So both of these are bent. That's not the question. The question is, which one has bond angles of 119? That's the question. Which one has bond angles of 119? And what do you guys think? Taylor?
We. Pass. I mean, SO2.
What did you say? You said pass.
Yeah.
Okay.
I meant SO2.
It is SO2. You need to pass. The reasoning it is SO2 is because there's 3 regions around electron regions. This double bond counts as 1. There's 3 regions around it. So this is going to be around 120 degrees. This one, even though they're both bent, this one's going to be around 109. So that's what it's asking. Yes, they're both bent, but which one's going to be angles of about 120? Number 7 we already answered. The lone pairs take up more space. On the back, the gist of that is showing that when you have a bigger molecule, like this is a soap molecule, the model of a soap molecule. Look at all those angles. They're making it with the angles being those 109.5 and everything. So for big dog molecules, even for this big sucrose molecule with 45 atoms, it's showing all those angles. So for big molecules, even like DNA that has hundreds or thousands of atoms, be thousands for DNA I guess, but Or for this is the rubbing alcohol in your medicine cabinet that you probably have. Those angles still happen. You're not gonna name the shape, but the angles still happen between them based on the number of lone pairs or bonding pairs and all that jazz. So that's what this is trying to get at. What are the approximate angles of each of these atoms based on the regions around them? That's what the back is trying to get at. So letter N, or not letter N, but this one right here, what do you think about this guy? Gus?
109.
109, and all they want you to do is say 109, 120, or 180. That's all that they're looking for you to do. And the reason why is because there's 4 regions around it. Remember, any type of bond counts as a region. What about this one right down here? Ellie? Sorry. Did I get that one right here?
For the top one?
This guy.
120.
Just that carbon. Yep. So this carbon's 120 because there's 3 regions around it. Yeah, the very top one up here is going to be 109. I wasn't pointing very well. The top carbon's 109 because there's 4 regions around this top carbon. And I'll scroll down real quick. And what about this guy right here? Deborah? 109 again. Yep, because there's 4 regions around it. What about this guy down here, Juliana?
I didn't get
Okay, look at the regions. How many regions do you think are around it?
there. 109.
Thank you, Ben. There's 4 regions around it? Yes. So look at the regions. Bonding 1, bonding 2, bonding 3, but the lone pair counts as a 4th region. So when there's 4, it's going to be 109. When there's 3, there's going to be 120-ish. When there's 2, it's going to be 180-ish. What do you think about this one right here, Amber? 120? Yep, because that lone, or that double bond counts. And then the very last one, Maddie, did you guys get this one? Maddie, did you get this one? Did you guys get that one? 180, yep. Yep, 2 total regions, 1, 2, so 180. So, just some practice, hopefully helpful, maybe not. You never know what you're gonna get. What we're gonna move into next is a demo. Demo. Come up here real quick. Someplace where you can see this water system. So if you're far away, maybe some of these people close by should stay sitting. Everyone else, whoa, you want to move and see something. Move and see. No. Move and see. All right. A few things. This is water. This is a Brett. That's what the name of it is. When I dispense it, it falls due to gravity when I open up the valve. So these water molecules, when I open up the valve, just tumble out and flow down. Okay? Now watch magic. This is there's a little bit of science here too. This is a comb. This is a piece of wool. Okay? When I rub the comb with the wool, what it does is I gotta think about this. The wool is easy to lose electrons. You ever wear wool and it's a little staticky? There's some clothing that gets really staticky compared to others. And it's because of its ability to lose electrons. So, sometimes some of those dry fit shirts, it's like clinging to you constantly. So there's some types of clothing that easily lose electrons, some things that don't. This guy easily loses electrons. So I'm going to transfer electrons to the comb. Okay? Right now this is going to be negatively charged because of this. Okay? Now watch. A little bit of magic. Some people will call me a water bender after this. One of the 4 skills of Avatar, being a water bender. So, this is negatively charged. It is attracted to the positive part of the water. It's partially science. Oops, I got 2 F's. So, it is attracted to the negative part of the water. If this was a non-polar liquid like gasoline, it would do nothing. It's still falling due to gravity, it's just that it's attracted to the comb, so that force of attraction is causing it to bend. So one of the, what was it, rock? Earthbender? I don't know, maybe, anyone ever watch those cartoon Avatar? Earth, Air, Fire, Water. So I have one of those skills. Now, what's happening? This is negatively charged because of the wool. What's happening are these molecules are tumbling out of the Brett, and the positive part, which is the hydrogens, are lining up. So while they're tumbling out, they're not lined up. But as soon as I put that negative charge there, they're going to line up and be attracted, and that's why they move towards it. But because this is polar, if this was gasoline, which I don't have any, but if I had some gasoline just sitting around, and I put that in there, it would do nothing. It just keep going straight down, no attraction whatsoever, because it is non-polar. So the polar non-polar thing has a lot of application, like this guy. And you're gonna see part of it, I'm gonna show you a little video here, you're gonna see part of the application. But this is soap. It's a model of soap. Pretty much all soap molecules, whether it's in your shampoo, your laundry detergent, your hand soap, or a bar of soap, or your dish detergent, has a molecule similar to this. Really, really non-polar, which will attach to like bacon grease or something like that. Really, really non-polar, or the grease in your hair. So you need a non-polar part. Sometimes they call them surfactants. But you need a non-polar part and you need a polar part. That's this. So this attaches to the grease, and then you rinse with water. The water attaches here, and it all goes down the drain when you rinse. So this is how all soap molecules, or how all cleaning pretty much works. They're maybe not all the exact same molecule, but they're close to that type of molecule. Sodium lauryl sulfate, something like that. If you look on that hand soap back there, it would be one of the first ingredients. So most cleanings would have a very similar molecule. Very similar. Maybe not the same, but very similar. Then there's other things in there to give it like a certain amount of smell, and sometimes there's different types of molecules, but the actual cleaning is going to be something like this. Alright. You can make soap a number of different ways. With some sort of fat and sodium hydroxide. The fat could be cooking oil, it could be lard from a pig, it could be human fat, it doesn't matter. Any type of fat and sodium hydroxide, you can make soap. So when you see soap, like at a craft fair or something, they're selling homemade soap, that's all someone's mixed together. We used to make it when I used to teach biochemistry. It's kind of a mess and stinky, but you actually end up with soap, good soap at the end. Alright, and it'll make. And based on what the fat, you end up with a different type of soap.
From that werewolf. Hey, those are good.
It'll make.
Another good movie gets slapped.
Alright.
Transylvania.
People.
I will look it up.
I'm going to show you this crash course, and he goes a little bit further than he has to, but the reason I keep showing it is because the fact that what he's going further into is a bunch of applications to the whole polar non-polar thing, which is good. So, got some good visuals again and stuff. He does talk fairly fast, and I know there's some Hank haters out there, but tough. There's some good things here. And then, really you're going to do simulation after this to kind of see if you can figure out when something's polar or something's non-polar. Monday we'll then apply it to the little structure sheet. I was thinking about doing that today, but time-wise the simulation takes a little bit longer, but that's okay.
Molecules. So many of them in their infinite and beautiful variety, but while that variety is great, it can also be pretty dang overwhelming. And so, in order to help this complicated chemical world make a little more sense, we classify, we categorize. It's our nature as humans, and it's extremely useful. One of the most important of those classifications is whether a molecule is polar or non-polar. It's a kind of symmetry, not just of the molecule, but of the charge. It's pretty easy to see when you're just looking at them. You got polar and non-polar, polar, non-polar, polar, non-polar. I'm going to take sides right now. I'm on team polar. I think polar molecules are way more interesting despite their wonky, off-balance selves. Non-polar molecules are useful and their symmetry has a kind of beauty, but polar... Alright, now here are two very different types of chemicals. Right here I have a stick of butter, and then in this bowl, that's just normal water. So I'm just going to go ahead and squeeze this butter, which if you're wondering is both a terrible and wonderful feeling. And then I'm going to just drop that. Now I'm going to attempt to wash that butter off my hand, but that is just not it's not going anywhere ever. It's just beating up on me. Why? Because water is a polar molecule and the various chemicals that make up butter are non-polar, and water wants nothing to do with that. So, what makes a molecule polar? Well, two things. First, asymmetrical electron distribution around the molecule. You can't have a polar molecule made up entirely of the same element because those atoms will all have the same electronegativity, and thus the electron distribution will be completely symmetrical. Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall Horan. They'll do anything just to be near it. Why? Some simple periodic trends. Electronegativity increases from left to right because there are more protons in the atoms, and more protons means more boys in the band. Meanwhile, it decreases as you... As the crowd of electrons get bigger, they start to shield each other from the effects of the protons. What I'm trying to say is that electrons are hipsters. If a bunch of other electrons are into that thing, they're less interested. Now, there are a number of other factors here, but just like the relationship between tweens and their latest boy band fixation, it's complicated and weird, and you probably don't want to think too much about it. But in this nice little map, you can see that the trend is pretty clear. The upper right is where all the superstars of electro fame are. Oxygen, nitrogen, fluorine, chlorine, and bromine are basically the one direction of the periodic table. So for polarity to occur in a molecule, you have to have two different elements at a minimum, and the difference between their electronegativities has to be 0.5.
Alright, so I'm going to stop right there just because it depends on the book. Your book says 0.4. Because of that, and since the final and stuff that they're giving you at St. Cloud State depends on the book, I want to make sure that we're all 0.4. So when we do this on Monday, as far as looking at the difference in electronegativity, what makes it a polar bond will be a difference of 0.4 or greater. So if the difference is less than that, the difference is too small, and the bond is going to be nonpolar. We'll deal with that more Monday, but I just wanted to throw that out because it's going to be
Or
different.
greater. If that's the case, the outer electrons spend enough extra time around the element that's more electronegative that chemists label the molecule polar. The result is a partially negative charge on the more electronegative part of the molecule and a partially positive charge on the less electronegative side. Now in extreme cases, like if the electronegativity is greater than 1.6, then we end up with two ions in the same molecule. This isn't what we're talking about here when we talk about polar molecules. We're talking about differences between 0.5 and 1.6. Another requirement for polarity, you've got to have geometrical asymmetry. CO2 here has the charge asymmetry locked up, but because the molecule is linear in a straight line, it's a kind of symmetrical asymmetry. The same thing goes for CH4 with its tetrahedron of weakly electronegative hydrogens around a more strongly electronegative carbon. These molecules have polar bonds, but the molecules themselves are not polar because the symmetry of the bonds cancels out the asymmetry of the charges. In order for a molecule to be polar, there has to be a dipole moment, a separation of the charge around the molecule into a more positive area and a more negative area. Lots of molecules are asymmetrical in both electronegativity and geometry. Those are our polar molecules, the asymmetrical beauties of chemistry. Look at them all. They're so quirky and weird. They've also got a system for indicating where their charges are. We draw an arrow with a plus sign at the tail pointing toward the negative side of the molecule. Little lowercase delta plus or delta minus.
Alright, just a real quick couple things. This is called a dipole. Also, you'll be drawing those on Monday. You'll be seeing them in your simulation in a little bit. These delta signs, this is a lowercase delta in the Greek alphabet. An uppercase delta in the Greek alphabet is a triangle, which in science means changing. Anyone seen that in a math class yet? A triangle like that, that just means changing. Okay, you'll see it in here at some point. But a lowercase looks like, I don't know, kind of like a D, I guess, for delta. But that means partial. It is not a full negative or a full positive because it's not ionic. If it's ionic, a metal would give it to the non-metal. We'd have a full negative and a full positive. The partial is because this atom has electrons around it more, and this one has it less. So we'll be drawing dipoles and all this stuff on Monday.
By the individual atoms signify a partial positive or partial negative charge. Liquids made up of polar molecules are really good at dissolving solids that are composed of polar or ionic compounds. Ionic solids are basically this polarity taken to the extreme, so far that instead of having a partial positive and partial negative dipole moment, the electrons have completely transferred, creating two charged ions. Now, I assume we've all heard that like dissolves like, so the easiest way to figure out if a liquid is polar or non-polar is just to dump it in some water. But the why of this phenomenon is usually just totally glossed over. What's actually happening to those molecules? It seems like they're all just bigots, terrified of anything even a little bit different than themselves. But this is chemistry, so there must be some fundamental reason, and if it's fundamental, it probably has something to do with decreasing the energy of the system. And indeed it does. Those partial positive and partial negative charges of water, they're at their lowest energy state when they're lining up together, positive to negative, into a kind of liquid crystal. There's an arrangement there. It flows, of course, but the oxygen sides are always doing their best to orient themselves toward the hydrogen sides of other molecules. You can even see the effects of that attraction as the surface tension that allows me to pour more than 100 milliliters of water into a 100 ml container. The strength of that surface tension depends on the intermolecular forces that pull molecules of a liquid together. These attractive, also called cohesive forces, pull the surface molecules inward. And what you see when you look at this pile of water is the result of those cohesive forces, minimized surface area in the water in this beaker. When you put a bit of oil into that mix, the water totally freaks out. Oils have notoriously nonpolar molecules, so suddenly there's this mass of uncharged gunk interfering with the nice orderly arrangement of polar water molecules. But if you take a closer look, the processes are very similar to those between water and air. Water does everything it can to minimize its surface area and kind of expels the oil droplets. Rather than the water disliking the oil, it actually dislikes itself much more, so it won't mix with the oil. Now if you put polar stuff in, water is all about that, and those polar water molecules go after whatever other partial charges they can find. Or, in the case of many ionic solids, the partial negative charges on the oxygen side all gang up on the positive ions, while the partial positives on the hydrogen side surround the negative ions, breaking the crystals apart and dissolving them into freely moving ions. In some cases, we can actually witness these interactions in unexpected ways. Mix 50 milliliters of water with 50 mils of alcohol, there's less than 100 mils of liquid. The arrangement of water mixed with alcohol is actually more structured and thus more dense, resulting in a smaller volume. The polarity of water also results in a phenomenon that makes life possible: hydrogen bonding. The partially negative oxygen and positive hydrogen atoms in a water molecule are not 100% faithful to each other. They engage in additional kind of loose relationships with other neighboring hydrogen and oxygen atoms. These loose, somewhat fleeting relationships are called hydrogen bonds. In ice, 100% of O and H atoms are involved in hydrogen bonding. The most energetically favorable spatial arrangement of these bonds actually pushes the water molecules apart a bit, resulting in the volume of ice being 10% larger than the volume of water. Really weird for solids and liquids. When ice melts, there are still about 80% of O's and H's engaged in hydrogen bonding, creating ice-like clusters that keep the volume of the cold water relatively high. With rising temperatures, these clusters disappear, while the volume of the truly liquid water rises, resulting in a major characteristic of water having its highest density at 4 degrees Celsius. And yes, that's why ice floats on lakes in the winter, and why the bottom of frozen lakes tend to be about 4 degrees Celsius, and also why hockey was invented, and why soda bottles explode when you leave them in the freezer. But hydrogen bonds are also why taking a warm bath is so great, why steam engines change the world. Temperatures on our planet are so constant when compared to other cosmic temperature fluctuations. It takes a lot of energy to change the temperature of water because each little temperature change or forming lots of hydrogen bonds. And they absorb or give off a lot of heat. In fact, the specific heat capacity of water is about 5 times that of common rocks. And amazingly, we haven't even finished talking about how powerfully useful these partial charges are. They also allow water to dissolve pretty much anything that's even partially nonpolar, which includes sugars, proteins, ions, and tons of inorganic chemicals. Water and its useful little dipole moment can dissolve more compounds than any other chemical on Earth. Frankly, it's amazing that it doesn't dissolve us from the inside out. Which brings me to one little last polarity tidbit: the hybrid molecule. There are lots of molecules, like the surfactants in soap, for example, that have both polar and nonpolar areas. Dish soap is thus able to dissolve the fatty parts of my butter catastrophe here, and then stick the polar sides out, allowing the whole mess to get washed away by Avogadro's numbers of polar water molecules that I'm sticking on my hand right now. Oh yeah, that's better. But not, I'm gonna have to go to the bathroom to get this all the way fixed up, so be right back. Likewise, the fatty acids that make up your cell membranes have polar heads, which keeps them interacting with the aqueous environment of our bodies, but non-polar tails, which prevent the cells from just being dissolved by the water around them. Pretty dang elegant, if you ask me. Thanks for watching this episode of Crash Course Chemistry. If you were paying attention,
It is pretty dang elegant. So, I have a new issue with my audio. There you go. Well, anytime. When you click on the simulation, the real ones don't work, so I put pictures of that. That's how they Alright, so I'm going to show you what you're going to be doing to try to, you're going to use a simulator to hopefully make more sense. So just look up here for now, and then I will show you what you're going to do. So on today's, that's not the one, that's not today. Today's Friday. But it's going to show up like this on your computer. Once you go to Real Molecules and click on it, it's going to say that, which is not fun. But just wait, just look up here, just look up here, just look up here, look up here. And see what you're going to, because of that, you're going to work with two atoms. It's going to tell you what to do and how to manipulate things, but you can move this around, you can see the partial charges, you can make the difference electronegativity greater, you can turn on electric field. So if it is polar, that means it has a negative end and a positive end. And if it has a negative end and a positive end, it's going to line up with the electric field, kind of like the water did with my comb. Now if it doesn't have a negative and positive end, it won't. It'll just sit there. Sometimes it spins slowly, but it will not line up with that electric field right away, which makes it non-polar. So you're going to do some practice with seeing what that looks like. Then you're going to do some 3-atom things. You can move it around, you can spin it around, you can turn on the electric field, you can change the electronegativity, all kinds of fun things. Partial, okay, fun. It's relative, but partial charges, bond dipoles, you can see all kinds of wonderful things there. But once you get to the very back page, it says Real Molecules, and that shows up. I was just told it's in self-service, but regardless, I have, because First Block it wasn't working, I have made a update in Schoology, so you just click on what you would see if you had that, because I was able to get it by changing my security settings, but you can't. But they said it's in self-service. I don't know what that looks like yet, but I might work on someone's computer and just see what that looks like. But you can see as an update for the very back page, there's pictures of exactly what it would look like. So, two things. I'm going to give you a electronegativity chart that you will be using if you need to know a difference in electronegativity. So you want to keep it someplace. You should know the trend, like up by fluorine, it's much higher. And then it's kind of like ionization energy gets way lower the further you get away from fluorine. But if you actually need to know numbers, you'll get to use this. If you actually need to tell the difference in electronegativity between two atoms, you will be using this sheet. Then, so just, that will probably be more used on Monday, I guess, but I'm going to have to hand out First Block, so I want you to be able to use that if you want. And then this is what you're doing. There are some color parts to it, so there's colored pencils out on the front table if you need it. So we're going to